Today we are going to be discussing technologies to make the stealing of passwords far more difficult for attackers. You have probably heard about passwords being stolen in large, high-profile attacks. Often attackers are able to get a dump of all of the passwords from the database, and from there they are able to simply break the passwords and get users' original passwords. This problem is compounded by the fact that a lot of users use the same username and passwords across multiple sites. We want to look at the techniques that can harden security of passwords in these situations where the password database is stolen. We will also look at how passwords are stored so you get a better understanding of how this process works. First, let's look at how passwords are usually stored. Most passwords are stored using hashing technology. The algorithms commonly used are MD5 or SHA, either SHA-1 or SHA-2. Hashes are meant to be one way. That means you can't take the resulting hash and derive the original plaintext password from them. When a user first creates their password, they type in the password they are looking to use. The computer then takes this plaintext password and runs it through the hashing algorithm, which outputs a hash. This is then stored in a password database or sometimes a file. To log in, the user once again types in their password, and once again the computer runs the plain text through a hashing algorithm and outputs the hash. The hash will be the same so long as the user typed in the correct password. If the user types the incorrect password in, they will get a different resulting hash, which means the computer will not let them log on. The computer then verifies that the hash in the password database matches the hash outputted from the original hashing algorithm, and if it does, allows the user to access the system. The idea here is that if an attacker is able to access the hash, they have no way of going backwards from the hash and producing the original password. This technology sounds great, but has slowly been getting weaker as the march of technology progresses. Computers have been getting faster. Smartphones today are faster than desktops from 10 years ago, and this trend will continue. This then allows an attacker to try random passwords, run it through the hash algorithm, and then eventually arrive on the correct password. While hashing prevents going backwards from the hash to the password, it doesn't stop an attacker from going forward a whole bunch of times until they eventually arrive on the correct answer. Passwords are often now broken utilizing video cards, as they are capable of breaking an incredible number of passwords in a very short period of time due to their capabilities of performing many computations simultaneously. In addition, storage is cheap. You can download so-called rainbow tables that have all the possible passwords and their resulting hashes in a large database that you can simply query to output very quickly. Then there is the human element. Users often pick poor passwords. One method of combating these issues has been to force users to choose larger passwords, but at this point it is no longer feasible to expect them to remember passwords of any larger lengths. The push to use web technology means we are centralizing our passwords into large databases that when hacked, an attacker is given access to millions of password hashes. Pictured is a diagram of how an attacker can derive a password if they have the resulting hash. To do this, they simply can brute force the password. Brute forcing a password means the use of a computer to rapidly generate possible passwords, run it through the same hashing algorithm, and then get the resulting hash. Once this is done, it is very simple to compare the resulting hash with the hash in the database and see if they match. If it doesn't, an attacker keeps changing the inputs. Eventually they will exhaust all possible passwords and therefore arrive on the password that has created the hash. A dictionary attack is a similar process, but relies on the fact that users tend to pick poor passwords. A dictionary attack tries a number of words that may be used and tries to use these as inputs, with the idea they'll have to try less total inputs in order to break the hash. One of the original techniques for protecting the passwords was a technique called SALT. Salting worked by generating a random value that was stored with the password database. This value was stored unencrypted. When a user would type in their password, the plain text password and the salt would be concatenated together. Salting prevents an attacker from pre-computing password hashes before stealing the password database. It doesn't prevent an attacker from guessing passwords after it is stolen, because if they are able to steal the password hashes, then they simply can also steal the salt as well. Again, remember, this is stored unencrypted. It also requires an attacker to break the password per user as opposed to all users at once if the salt is unique per user. Salting is still considered a good practice, and we'll see that other technologies use salting as well in addition to the technology and protection they provide. Let's look at PBKDF2 and bcrypt next. The idea behind both of these is that hashing algorithms were built for performance and chosen because they were fast. If we can make the process of brute forcing go from days to years or even thousands of years, then it doesn't prevent an attacker from brute forcing the passwords, but it does make it a whole lot more difficult and maybe not practical. In addition, it may be possible to have dealt with the breach notification before the attacker is able to steal the passwords. This process is called key stretching, or making the process take longer so that the key is strengthened. It still isn't impossible. It is just a lot more costly to the attacker in terms of the time and money they would need to invest in breaking your passwords. The first technology is bcrypt. Bcrypt uses a stage in Blowfish where the key setup was performed. The reason this was chosen was due to how slow it was, and it was specifically a difficult process for video cards to perform. To generate a bcrypt value, you take the password, combine it with a salt, and then take a work factor. The work factor increases the amount of time it would take to generate the output. The work factor increases exponentially, so going from a work factor of 1 to 2 takes approximately twice as long. As a designer of software, you need to balance the security of the hashes with the extra work that you'll be placing on the systems, as the authentication process will now take more time as a whole, and you may require additional hardware to handle this extra load. Here is a random image I found on memegenerator.net. bcrypt works by taking the password and the salts as inputs. It then runs it through the key setup process and generates an output. The work factor tells it how many times to repeat the process, a number of times, until it finally gets to the final output, which will be how your password is stored. scrypt is another technology that's very similar to bcrypt, but also allows you to burn more memory on a computer system as well. This means the attacker will need to invest in large amounts of memory if they want to attempt to brute force the passwords with any efficiency. An interesting tidbit is that a lot of cryptocurrencies, such as Litecoin, use the scrypt process. PBKDF2 is a technology that takes other algorithms, such as hashing technology as well as HMAC, and simply says to repeat this process a given number of times. A designer chooses the number of times to repeat the algorithm, and PBKDF2 keeps repeating this number of times. NIST recommends using PBKDF2 in conjunction with other NIST certified algorithms such as SHA-2. The current recommendation is SHA-2 256 10,000 times. As computers get faster, it will be possible for designers to simply increase the number of times, making it harder for attackers to brute force as computers grow in capability. The PBKDF2 algorithm takes as inputs the password, the salt, and the number of times you want to reiterate the algorithm. Finally, you can also change the desired length of the key if desired. Example I show below in the slides is WPA2. WPA2 uses HMAC SHA-1, a passphrase, the SSID, which is the salt, the desired length, which is 4096, and then the generated derived key is D256. So it's demo time. I wrote some simple programs that utilize the different algorithms, including bcrypt and PBKDF2, just to give you an idea of how they work. So I've written the programs in bcrypt. So in Unix, you can write the words time and then the program to run, so SHA-512, and we're just going to SHA-512 the word password. And we can see here that total it only took fraction of a second, so 0.078 seconds. So this is SHA-512 without any of the hardening technologies we've talked about. But now let's look at bcrypt. So we're going to run bcrypt, and we're going to time the amount of time it takes. We're going to again use the password for the original password and send it through the algorithm. And we're going to use a workload or a work factor of 12. And we can see that it takes about 0.3 seconds, significantly longer than SHA-2 by itself. Let's increment it up to 13. And we'll see here that now it takes approximately twice as much time. Again, we're seeing it exponentially rise. If we move it up to 14, we should once again see it almost double, and now it's about 1 second. So as a designer, you need to balance how long you want your authentication process with how difficult you want to make for breaking your passwords. So once again, now we're going to be looking at PBK DF2, and we're going to be timing how much time it takes to run each one. So in this, we're going to run PBK DF2, and we're going to use the password, but this time we're going to use 10,000 times. And we can see it takes about 0.1 seconds. If we say double this, we'll see it takes a little bit longer. And we can just keep incrementally increasing the amount of time it takes in order for it to do it. So at 200,000, it takes about 1 second. And you would balance this with how hard you want your passwords to take. When implementing these technologies, here are some details you want to consider. If you make the process take too long, it may be easier to denial of service your systems by simply entering large number of passwords and putting more load on your servers. Look for other technologies to deal with this, such as denying a specific IP for a given period of time after a certain number of failed logins. A CAPTCHA would be another technology that may be beneficial. Finally, store the work factor or iterations per user in the user database. By doing this, it will be possible to increase the difficulty when a user changes the password so that as computer technology progresses, the difficulty of cracking the passwords will as well. Thanks for watching. I'm Daniel Lowen. I have a website at securearchitectures.com that I periodically update. Please check it out. I do add some interesting tidbits of knowledge on there, and I will be posting more videos. I have also posted the Python scripts there if you're interested, so do check that out and just search for password technologies on the blog, and you will find this post this video as well as links to all the scripts. Thanks for watching and keep on learning.